Okay, good afternoon, everybody. This is a climate and atmosphere research colloquium in the University of Iowa, and I'm glad to introduce to you our speaker, Jans Wiedemann from the University of Oklahoma. And I have known Jans for almost 20 years. My first paper as a graduate student, actually, he was a co-author on it, and he helped me on getting some aircraft data to validate my LD retrieval from a GOSAT satellite. I was like in 2010, 2001, sometime about that. So later we see each other a lot in different meetings and the conferences and the panels. And he has been he graduated from the UCLA with PhD in meteorology atmosphere science in 1999. And then after that, he joined the NASA AMS and has been leading in multiple fronts the different efforts for NASA's Earth observations as well as aircraft campaigns. Before he moved to Oklahoma as a director for School of Meteorology, which by the way is the largest one in the country, to study weather and the atmosphere. He was the PI of the NASA's EVS-2 project called Oracles, which has been collectively has involved many scientists, including some of our folks here. So it's my great pleasure to introduce Jans, and thanks for him to give us a talk. So Jans, take away from here.
All right. Well, thank you very much, June, for the invitation. It's a great pleasure to be here. It almost feels like a real visit after visiting with your groups this morning. That was great. I really appreciate the invitation, and I hope that I can reciprocate, or we can reciprocate here at OU and have some of you come to us and maybe have this be the beginning of a fruitful research collaboration. I've only put my own name on here because at some point co-author lists of 60 or 70 people become just ridiculous. Just like in the beginning when I met June, I greatly value and benefit from collaborations with people much smarter than me. So I was always sure June was going to do well in this field. I wasn't so sure about myself when we first met, but here we are, a mere 20 years later. So it is my pleasure to introduce the CLEAR research group that I'm a part of at OU. Over here on the right-hand side, we have Ian Chang, Connor Flynn, and Lan Gao as the senior research members of the group, research scientists, and Connor's case, senior research scientist. And then my first ever 3 graduate students, Emily Lenhart, Logan Mitchell, and Sean Spratly. And for those of you who don't know, we actually have increased the number of people working on things other than severe weather at the University of Oklahoma. Down there are 3 faculty members that have, in Marcella's case, recently joined the school. Feng joined, I think, 2 years ago now, and Greg McFarquhar has been here the longest. He's been here for 4 or 5 years, but suffice it to say, the aerosol cloud and aerosol cloud climate interaction work that these groups do is somewhat new to OU, and I'm going to conclude this talk by telling you a little bit more about this school. Because I'm actually also the director of the School of Meteorology, and that takes up a lot of my time, which is why I have all these capable helping hands. So for backgrounds, I'm going to go over what I call some deficiencies in climate models that we have some hope to address with observations. By training, as June mentioned, I'm an observationalist. I came from NASA, where we flew airborne instrumentation and used satellite measurements to look at aerosol cloud climate interactions. And when I speak about deficiencies in climate models, it means no disrespect. I'm trying to paraphrase what I see gaps that we can address. It is by no means criticism of the model or modeling efforts. They are exactly what we need to do, and there's fantastic work being done. Just from an observationalist point of view, I'd like to be up on what can be improved and what constraints can be provided by observations. So I'll talk a little bit about recent field deployments, most notably the Oracle's campaign that we just closed out, a campaign to the Southeast Atlantic to study biomass burning, cloud interactions in the Southeast Atlantic. I'll use one slide because I was expecting this to be an engineering group, and so I'm going to talk about instrumentation for one slide because we were rather proud of a new instrument that we built at NASA Ames before I left. And then I'll provide some of these comparisons of models and observations and what we have learned from them. I'll then do a complete 90-degree turn and talk about the NASA Atmos mission, which was formerly known as the ACCP mission. It's a mission that was recommended by the Decadal Survey. It is arguably the largest aerosol cloud mission that NASA has ever attempted. It's slated for launch in the late 2020s. And your own Greg McFarquhar is a heavy contributor there, so you may or may not have heard many of these things. So I'll tell you a little bit about the remote sensing approaches that we're developing for that, and also how we've applied them to suborbital data. And as I said, another 90-degree turn to tell you a little bit more about the School of Meteorology. Okay, I just love this animation because it induces humility in my thinking here, frankly. What you're looking at is a GEOS 5 model out of NASA Goddard with many contributions from others, visualizing 4 major aerosol types and how they're moving around in the Earth system. In blue, you have sea salt aerosols. In white, sulfate aerosols. In green, biomass burning or organic plus black carbon, and the orange reddish colors are dust. And it becomes rather quickly obvious what the major problems are. In order to understand the impacts of these emissions on air quality, on climate, possibly even on weather, we have to understand the meteorology that drives them and moves them around in the system, in addition to understanding the processes that they undergo during their transport. In very unfortunate situations, you have mixing of multiple aerosol types. If you look down here, every once in a while, you see a nice mixture of dust, sea salt, and sulfates mixing with organics from fires in Southern Africa. So it is a messy system, and it's no wonder that we're struggling to reduce the uncertainties in climate forcings due to anthropogenic aerosols. This is background, and I'm going to go over this quickly given the audience, but as you well know, aerosols have a direct effect on climate in the system by scattering and absorbing shortwave incoming radiation and outgoing radiation. They do interact with clouds and change cloud properties. And in the long wave part of the spectrum, we have large aerosols, most notably dust, interacting with outgoing long wave radiation. And we have all kinds of potential other secondary effects on surface albedos and other sources. So I apologize for putting up an IPCC chart. Everybody's tired of this chart, but I'm going to throw a few numbers at you or things at you that you may or may not have known, because if you only stare at this, you may not know that, for example, the uncertainties in the radiative forcing due to the well-mixed greenhouse gases in red over here, most notably CO2, actually are twice as large as they were in the previous IPCC report. So this is the result of the IPCC report published in 2013. And it turns out that the cloud responses due to this warming from greenhouse gases was so poorly known that we had to increase the error bars on greenhouse gases. What you probably do realize is that the positive effects here, the warming, is largely offset by negative, meaning cooling effects due to aerosols in 2 blue bars on the bottom here, where the first bar speaks to the direct aerosol radiation interaction, and the second one to the aerosol cloud interactions. Including the cloud adjustments, both of these effects are rather uncertain. And if you look at the total uncertainty in the total anthropogenic forcing of climate, you see that the uncertainties in it, this black bar down here, is mostly driven by the uncertainties in the aerosol effects. And in a bigger picture, of course, it turns out that these uncertainties in aerosol climate forcings are the main drivers of the uncertainties in climate sensitivity, that and cloud feedbacks, of course. So we are well advised to reduce these uncertainties. Another slide from IPCC that illustrates the effects. We're talking about, again, the direct effect by which aerosols scatter radiation back to space and have a cooling effect. If aerosols are absorbing, you have something that we call the semi-direct effect, by which if the aerosol is located above clouds, you can stabilize the atmosphere and inhibit mixing into clouds and change cloud lifetimes through that, or cloud cover below. If the aerosol is directly inside the clouds, you may have a cloud burn-off effect, something that Andy Ackerman coined first, I believe. On the aerosol cloud interaction side, over here on the right, you have this effect by which if you introduce aerosols into clouds, they usually become changed in such a way that there are more and smaller cloud droplets, which, all other things being equal, mostly liquid water path being equal, changes the brightness and the reflectivity of the clouds to space. And then you have effects by which the suppression of rain can change the lifetime. And you have also glaciation effects potentially that change severe weather, deep convective storms. So the most dramatic illustration of indirect effects, of course, are ship tracks. So if you look at stratocumulus cloud decks of the world, you see these streaks every once in a while, and they represent essentially ships going underneath and the exhaust from ship stacks being ingested into these clouds and having exactly this cloud albedo effect, meaning smaller, more numerous cloud droplets. Okay, some deficiencies in climate models, and again, I mean this with all respect. If you compare for different aerosol species, in this case sulfates, the vertical distribution and how it's represented in different models on the left-hand side here, you will find that the different models, even in the global mean, have rather different vertical distributions. So this is just normalized to the surface mass mixing ratio, in this case, again, for sulfate. And you can see this drop off in sulfate with altitude in most models, but really the individual models are rather different. So what I find interesting about this paper by this group is that they then try to compare what happens if you take an individual models and turn on and off certain processes, which are very much like the people who are in your guys' groups. You do the same numerical experiments essentially. And the upshot and what they pointed to was, well, you do get all kinds of different vertical distributions, but some of the vertical distributions you cannot get from an individual model by turning on and off different knobs. And their conclusion was that there are inherent model differences still that control the aerosol vertical distribution, such as convective transport, in-cloud scavenging. This dashed blue line, of course, is a convective transport that has a dramatic effect on the vertical distribution, of course. But what they're saying is, because this single model, by turning all the knobs, can still not represent all the other modeled vertical distribution. That means there are model-to-model differences in fundamental physics of it, in the model, as I said, with regard to some of these processes. I come from the radiation side, admittedly, and it turns out that over years past, we've had to increase the black carbon concentrations in models to match what we call Aeronette retrievals of absorption optical depth, mostly due to black carbon. Aeronette is a globally federated network of sun photometers, some 200 sites or so that operate continuously now. And one of their most important derived products, which they get from inverting the direct beam and the sky radiance measurements, is what is called the aerosol single scattering albedo, which is the ratio of scattering to extinction, extinction being scattering and absorption due to aerosols. The single scattering albedo, it turns out, is a very, very important driver of top of the atmosphere radiation balance in such a way that it depends on whether it is a warming or cooling effect on climate based on the albedo of the surface plus atmosphere system. What you're looking at here are top of the atmosphere flux changes induced by aerosols for different aerosol types with different single scattering albedos. For example, the black one here is a non-absorbing aerosol with a single scattering albedo of 1. And it always has a cooling effect on climate, regardless of the reflectivity of the system underneath. But as you increase the absorption, meaning you're decreasing the single scattering albedo, you're moving to the left with this critical point here at which the top of the atmosphere effect changes from a warming to a cooling. So the top being the warming and the bottom being the cooling effects. So depending on the single scattering albedo, the seen albedo at which this switchover happens depends very much on the single scattering albedo. If you look at the single scattering albedo observations from Aeronette, though, you find some interesting results. For example, that if you plot them at some of the stations against aerosol optical depth, so the total loading of aerosol, you see somewhat of a systematic trend, such that the aerosol become less absorbing, meaning higher single scattering albedo with increasing optical depth. Now, there are physical reasons why that could happen. Water uptake, for example, would not make the aerosol more absorbing. But it is, if true, an interesting effect. And the important thing is that Aeronette divides the world into optical depth greater than 0.4, and only at that optical depth do they assign the highest quality criterion of level 2. There are great questions about the representativeness of these measurements. A recent study by Nick Skutkins found that the AAOD representation errors for some of these sites can be greater than 40%, meaning that at the few times that you measure the absorption optical depth and you average it out for the year, and then you compare it to, for example, a model. In an Aussie study, you will find that the subsampling can give you errors of greater than 40%. And given the importance of this factor, this is a really big deal. So let's see what models do with single scattering albedo. Here, a recent study by Brown et al. Shows the single scattering albedo plotted from a number of different field campaigns, plotted against the ratio of black carbon to total carbon in aerosols. And you see this general trend that with increasing black carbon content, you have decreasing single scattering albedo. Okay, they then looked at 8 different models, each one of these plots being a different model, and broke the world down into 5 different regions. That's what the colors are essentially. And looked at how do their single scattering albedos in the models compare to this cloud here of measurements from field campaigns, which are then being given over here as these gray clouds behind it. And by and large, you see that essentially most of the models make the aerosol too absorbing, interestingly enough, in most parts of the world, meaning they have a lower single scattering albedo for a given black carbon to total carbon ratio. And that likely has to do with uncertainties in the aerosol life cycle and its impact on absorption. There are some processes that we feel are not well captured in models, as again, many of you running these models are well aware. So the paradigm for addressing this is to look at suborbital observations and satellite observations, which is more our group's domain, to what the models do. And really there is a very complementary nature of how we're trying to get to these aerosol effects on climate, essentially. So the suborbital data is generally much more accurate than the satellites, but it's much more sparse also. The satellites can be used to test models, but they do not provide some of the constraints that the models need to improve the parameterizations of processes. And that's where the suborbital data come back in again. But if you do that with a suborbital measurement data set, you need to make sure you understand how the measurements that you're taking for a brief period of time and at very high accuracy, how that fits into the PDF of the aerosol properties you're trying to capture and constrain. So it is a very intricate interplay between all of these different aspects, the satellites, the suborbital data, and the models, and how they're being integrated against each other. And I spoke to Aeronette already, which is one of the main staples of the suborbital observations, of course. Okay, slight detour. I was told that I've coined the term model relevant observations. I was 100% sure I saw that term in a NASA announcement of opportunity. And when I looked for them, the idea is there, but it never really is fully in there. So Objectives for suborbital Earth venture proposals, for example, there's language that reads, the overall objective can be met in a number of ways, including but not limited to making measurements that address weaknesses in current Earth system models. And you look all throughout the calls and you find language like that. My personal definition of a model relevant observation is that it has to address directly a deficiency in a model. It has to provide sufficient accuracy to help constrain the model processes or deficiencies. And then you have to provide your measurement or your observation at a sampling that is sufficient to address the model deficiency. If you only measure something every once in a while and you have no idea how that fits into the PDF of the model world, you are unlikely to have a model relevant observation. This speaks to sampling, but I'm really going to go over this very quickly. What you're looking at is a comparison of latitudinally averaged aerosol optical depth from an observation that I don't have time to describe in black here, but it's a multi-satellite sensor observation using MODIS, OMI, and Calliope, and comparisons to two different models. So the models are different on the left and on the right. And what we've plotted in the thick red line is the full model at full sampling, which is why it's fairly smooth. And then we subsampled the model at these available satellite observations, and we've plotted that with red crosses. And you see that there are sometimes differences, significant differences between the full model sampling and the subsampled modeling. So in my mind, if you really want to learn something about the model, you can only look at places like here on the right-hand side, where the subsampled model and the model at full sampling agree with each other, such that if an observation disagrees with it, you really have a cause to change the fundamental properties of the model so as to bring your model into better agreement with the observation. The other reason, of course, why I'm fairly confident that this peak in AOD here for this December, January, February timeframe and is rather real is that this model reproduced it pretty darn well. This model did not. But on the other hand, there are sometimes differences where you can fool yourself. You have an observation over here in black at 30 or 40 degree north that agrees really poorly with the observation again. But if you subsample the model to the observation, you see all of a sudden you have good agreement. And so there's no need to change your model here. This difference in this case is entirely a sampling problem. And I know people think about this, but I'm not always sure that people pay enough attention to this. So let's shift gears and talk about the Southeast Atlantic. The system sets up in such a way that you have pretty consistent biomass burning between July and October, producing about 1/3 to 40% of the global black or carbonaceous aerosol mass in the world. That's shown by these fire frequencies over land here in green to red. And then this aerosol gets transported out over the ocean where it gives rise to an optical depth plume that's given here in these yellow to red colors. And between July, August, September, and October, this plume moves southward as the flow gets more zonal and the fires move slightly further southward. The blue open contours are contours of cloud fractions. Turns out that this is one of the 3 places where we have a semi-permanent stratocumulus cloud deck on this planet. And the interactions between the biomass burning aerosol and the cloud deck are exactly what was the main driver for this oracles campaign that I'm trying to motivate. Vertically resolved, we think that the aerosol gets injected fairly high in the atmosphere over land, and with the South Africa easterly jet gets transported out over the water, where under general subsidence it gets pushed downward, and with an increasing marine boundary layer depth, you have more and more chances of actual physical interaction between the biomass burning and the cloud deck. And it turns out that this is a rather simplistic way of looking at it and not really at all what's going on. Okay, the deficiencies in climate models in the Southeast Atlantic are shown in this figure here. On the left-hand side, you're looking at aerosol radiation interactions from 16 different models. In blue, you have cooling of climate. In red, you have warming of climate. And you can see that between these 16 different models, there's absolutely no agreement in the regional distribution of the aerosol radiated forcing. So this is a direct effect, which of course doesn't mean the aerosol is wrong necessarily in these models. It may very well be that the underlying cloud deck is wrong, as I spoke earlier about the interaction of, especially for an absorbing aerosol, with the brightness of the underlying scene. So it could very well be the aerosol or the clouds being incorrect, or the aerosol or cloud properties being incorrect, why this radiation aerosol interaction is not represented properly. On the right-hand side, we have the same idea for two different models looking at aerosol cloud interactions. This is the same model with a different cloud microphysics scheme. And you see that they too disagree by a factor of 7 or so, just by changing the cloud microphysics assumptions in the same GCM. Okay, so we said, okay, let's try and study this further with a set of suborbital observations. We took the NASA P3 aircraft and flew from Walvis Bay, Namibia in 2016, and from Sao Tome, because we were kicked out of Namibia in 2017 and 2018. And in 2016, we also flew the ER2, which is a NASA aircraft that usually carries remote sensing payload. We successfully flew 15 P3 flights in 2016, 12 ER2 flights, and then 13 and 15 flights respectively in 2017 and 2018. We coordinated with several international field campaigns, a ground-based DOE-R mobile facility deployment called LASIK to Ascension Island, which is over here. And in 2017, there was also a French deployment to Walvis Bay, Namibia, and a British deployment of the Met Office to Ascension Island, basically, and we did some intercomparison flights. We established a number of new Aeronette stations. Only 2 of them were paid for by oracles, but about a half a dozen more were established in the source regions that are not shown here. And from the get-go, we involved modelers who work at different scales, meaning LES to WRF-Chem to GEOS-5 at the conceptual stage of designing the field campaign. And as you all know, Greg and Gonzalo were active members of this modeling group supporting oracles. Importantly, half of our flights we devoted to what we call routine flights, which are flights along exactly the same ground track, only varying vertical, the altitude of the flights. In 2016, and I'll talk about that later, it was this diagonal. In 2017 and 18, it was a north-south flight, basically. And about half of our flights, we flew along those. Here's some instrumentation information. Suffice it to say that certainly on the aerosol side, on the remote sensing in 2016, we flew the best information that's out there, including HSRL2, which is a high spectral resolution LiDAR, very capable, MODIS airborne simulator, and 2 types of polarimeters, and flux radiometers. And then in 2017 and 18, we moved the HSRL and the RSP instrument onto the P3. And there are a number of other instruments that also, the red ones here are remote sensing, in case you're wondering, and the white ones are cloud and aerosol in situ measurement. The only gas phase measurements we took were CO2 water vapor from a Pizarro instrument that Jim Podolsky flew. Okay, so let's talk about some results. One of the most outstanding results is that we found a pretty reproducible vertical distribution of single scattering albedo in each one of the years. So you're looking at campaign averaged in August 2017, September 2016, October 2018, single scattering albedo vertical distribution, such that the lower we went in the plume, and that's why it ends at about 1 to 1.5 kilometers, we didn't go into the cloud deck. At least this plot doesn't show our going into the cloud deck. We did that for in situ measurements of clouds. But here we're showing the in situ measurements of aerosol and this vertical gradient in single scattering albedo, such that the aerosol becomes more and more absorbing with decreasing altitude. The smoking gun here is that if you look at the aerosol chemistry, the black carbon to organic carbon ratio sort of showed an increase with black carbon with decreasing altitude. And that's attributed essentially that vertical that the transport is such that the lower part of the plume tended to be the oldest part of the plume, meaning it had most time for aging. And that will become relevant as I move forward here in this presentation. Here in particular are plots of the ratio of total to black carbon in the top as a function of model-derived mean plume age. And you can see this decrease of total organic carbon relative to black carbon. And you see that this is not a loss effect in that the black carbon to CO ratio is rather constant with plume age. So it turns out there's a half-life of total carbon. There's a carbon loss mechanism that scales up between 6 and 8 days. A half-life of 6 to 8 days or so is the ring down time of this total organic carbon. Meaning the black carbon stays behind, the total carbon in the shell gets lost, and that makes the aerosol more absorbing. And that's shown in this plot here, where Art Sedlicek is trying to combine these measurements from multiple campaigns. The oracles one is in the upper right-hand corner of this plot here, and I'll tell you what that is in a second. And on the right-hand side is given versus plume age. What you're looking at is on the left-hand side, the distribution of coating thickness relative to core size, essentially. In plot A down here, this is very near fires in an experiment called Bebop. Up here, it's about a half a day old in an experiment called NBO. And then Oracle shows something, and then far field LASIK downwind from Oracles on Ascension Island, you show these coating thicknesses. So what you see is that essentially with some aging, the core grows a little bit, but it's essentially the same. What really happens is that you're in the initial stage, you're growing your mass ratio of shell to core. Then there's a stagnation period, essentially, and then you are losing the shell, and the core remains. And that's sort of shown on the far field here, where the coating thicknesses are thinner and thinner the older the aerosol gets. And that has an implication for single scattering albedo. If you leave behind an absorbing core to an absorbing particle with a shell, then this aerosol is indeed becoming more absorbing. So this is very much corroborating the story that we looked at before with the total organic carbon to black carbon mass ratio loss. Okay, I still care about radiation, and I know just enough about these microphysical processes to motivate development of instrumentation. I put this in here for June because June has asked me for data from this instrument called 4-star about, I don't know, 3 years ago, and I still have it on my to-do list, but it never makes it higher than number 15. And I just wanted to speak about this. So at NASA Ames, we developed a number of airborne sky scanning, sun tracking, sun photometers. So these are instruments that do the same thing that an Aeronette instrument does from the ground, which is to measure the brightness of the direct solar beam and the brightness of the sky. But it does it from the aircraft, from the P3 to be exact. And a number of problems have to be solved for that. But it also then, we took several steps. So we have this optics that does the sky scanning and sun tracking. But also as detectors, we are using rack-mounted spectrometers now, which then allows us gas phase retrieval. So we can retrieve columnar water vapor, NO2, and ozone. We've demonstrated that, and we're hoping to push retrievals to other trace gas species. And as I said, these other optics then allow us a measurement of sky radiances, which are shown down here as an example. What this instrument does, just like an Aeronette sun photometer, it gives you a retrieval of single scattering albedo. And what you're looking at on the left-hand side here is a case study of single scattering inner comparisons from a whole slew of different instruments. And you may or may not know them by their acronyms. So the 4-star instrument that I just described are these blue values, for example. The classical way of doing this is by flying a PSAP instrument, which is a absorption photometer, and combining it with scattering measurements from a nephelometer, and that's shown in green. AIR-MISPI is that airborne imaging polarimeter, and you see retrievals of that here from Fangzhou in pink. And the black is a retrieval from sky irradiance measurements combined with optical depth from the SSFR instrument. And the remarkable thing really is, if you think about how different these measurement technologies are and the approaches, that we have this grouping of single scattering albedos of 0.03 or so at 500 nanometers, no bigger than that, which is remarkable. And then when you look at campaign averages down here on the lower right-hand side, you see some differences, but those may very well be because the instruments are not always co-located. I mean, this case study on the left here required the ER2 aircraft to fly right on top of the in-situ aircraft, of course. Okay, so how do the models do with some of these things in the Southeast Atlantic? You are looking at, on the upper left-hand side here, a map of grid boxes that we have set up along the routine tracks. Again, in 2016, this diagonal. In 2017 and 18, this north-south oriented flight track. And down here, you're looking at the comparison of observations in the red bars against 4 different models. There's the WRF-CAM model that Greg and Gonzalo and Pablo Zaide were involved with. And then there's the unified model from the UK, the Aladdin model from the French, and GEOS 5, I missed one. And you can sort of look at the PDF of single scattering albedos along these routine tracks. And you can learn something from these. I won't go into the details, but let's just say between the models, there's quite a spread. Some overestimate in single scattering albedo by the Aladdin model, some pretty good performance by WRF-CAM, I would say, but the unified model down here does pretty well as well. And you can do this basically for other models as well. And down on the right here, I'm showing a MERA-2 comparison of spectral single scattering albedo, which was surprising. Lon and Ian recently produced this. You can see that regardless of wavelength between 400 and 995 nanometers, the MERA single scattering albedo is pretty close to the 4-star derived values. So there's even agreement in the spectral dependency of single scattering albedo. In terms of vertical distribution, comparing some of the models to the observations, I'm just giving you the routine track comparison along the routine track. Every one of these plots up here is vertical profiles of extinction in one of these blue boxes along this diagonal track. And again, in red, the observations. Take-home message at first, I would say, and I thought of this when Gonzalo showed this morning an increase in the emissions potentially. I would argue that almost all models show less extinction in the plume than the observations indicate here, and that's given in red. And then you look in the boundary layer and you see that most of the models have more extinction there than the observations in almost all of the boxes. Some of that is due to the fact that these are dry observations and that the model is either dry or ambient. Only the unified model is actually given here. And you can see that the difference between the unified model, dry and ambient, is rather large. So a good deal of the difference between the extinction and the boundary layer between observations and the models is due to humidification, undoubtedly. The other thing, though, if you're looking at the problem in the Southeast Atlantic, is a problem that's called too few, too bright in climate models regarding clouds. Climate models are known to underestimate the amount of low-level stratocumulus clouds and to then have to make them brighter in order to fix the radiation balance. So on the left-hand side, you're looking at cloud fraction, warm cloud fraction in these grid boxes, and now compared to MODIS satellite observation and Severi satellite observations. And you can see that most of the models underestimate the cloud fraction, with the exception of the WRF-CAM model, which is pretty close to the observation, if anything, a slight overestimate potentially. And then on the right-hand side here, this is cloud optical thickness, which is somewhat synonymous with brightness. And you can see that most of the models are certainly the UK model has to make the clouds much brighter in order to make up for the fact that they had too few of them. So this is a known climate problem, and I don't have the full grasp of the maybe Greg or Gonzalo can comment on whether this is towards solving some of the problems. So I did not mean to suggest that this is due to aerosols. They may or may not play a small role. It's more likely that it's actually the treatment of upwelling ocean currents that the models do not get right, is actually my understanding, because the low-level stratocube actually get driven by that. Okay, let me see how much time I have to get into the details. One of the paradigms of oracles was that we wanted to stitch together the seasonal cycle of the biomass burning season by going in different months each one of the 3 years that we deployed. And we thought, well, it's hopefully the interannual variability is small. Well, it turns out that's really not the case. What you're looking at here are the fire counts and above cloud optical depth retrievals that are climatology. So I think that's something like 15 years from Modus Aqua. And you can see that, the biggest plume here is in August, and September is a little bit less, and October is a very faint plume. And then on the right-hand side, I'm plotting each one of the deployment years. So 2016, 17, 18, August in the top row, and then September, and so on and so forth. And you can see pretty large interannual differences, such that when 2016, for example, when we didn't go, there was a large above cloud optical depth plume. 2017, it was probably smaller than the climatological mean optical depth. 2018, it was a little bit larger again. And similar differences year to year in the other deployment years too. So you have to be very careful and use the models to tell you about the interannual variability if you want to stitch together a cycle from the different seasons. So specifically, the story plays out a little bit like that. In each one of these panels, now I'm going to compare the climatology to the deployment years. First, zonal winds are down in 2017 in August. In 2016, zonal winds are down essentially. And again, this is important because that's what drives the transport of the aerosol outward. And in 2018, they're about similar to the climatology. So when I say the winds are down, that's again by comparison to climatology. If we look at above cloud optical depth, low cloud fractions and fires, we see that in the deployment year, August 2017, fires are up. They're probably a little bit stronger than climatology, but the above cloud optical depth is down, interestingly enough. In September 2016, fires and above cloud optical depth are similar to climatology, I would argue. And in 2018, fires and above cloud optical depth are probably up by comparison to climatology. If we now look at cloud droplet number concentration as a measure of how polluted the boundary layer clouds are, we would say that in 2017, the deployment year, probably the clouds are more polluted than the climatology would indicate. So CDNCs are up. In 2016, we have about the same pollution level in clouds as we do versus climatology. And in 2018, again, I would argue that the cloud droplet number concentrations are up. So the interesting story is really, in my mind, that in 2017, we have a smaller above cloud optical depth plume, but more polluted low clouds, which could speak to the general fact that this year may have just been one where you had more mixing into the boundary layer. Overall, oracles really does provide this view of the vertical structure that we have not seen before. From Calliope, it was very difficult to see the bottom of these plumes and how often they were in physical contact with the low-level clouds. And the HSRL system that we flew on the ER2 first and then on the P3 just gives you so much more detail such that you can see if and when there is contact and when there isn't any contact. I won't go over that. I've spoken to that to some extent, but our boundary layer CCN observations basically corroborate this picture that 2017 was unusually polluted boundary layer in terms of number concentrations of CCN, which would corroborate this polluted cloud droplet number concentration peak by comparison to other years. Overall, of course, oracles is a test bed for remote sensing instrumentation. I really can't do this figure justice, but we have one of the most advanced HSRL LiDAR system, one of the most advanced radar system, three wavelength WKA KU band radar. We have imaging and straight line polarimeters, imagers, solar spectral flux radiometers. We had 4-star. It's an embarrassment of riches in terms of instrumentation, and you can read a little bit more in my overview paper that I referenced down here. Essentially, one of the joint retrievals now combining RSP, which is a polarimeter, and HSRL2, which is the LiDAR, was done by Feng Zhu here at OU. This is basically a real data analysis where you're combining the suborbital data to see the information content. And the study showed rather good ability to retrieve vertically resolved single scattering albedo and effective radius of the fine mode from this combination of LiDAR plus polarimeter. Apologize that I have to fly through that a little bit. I wanted to give a big picture really quickly about recent major aerosol IOPs because I had to do this anyways. So here are some of the state of the art, either in terms of coverage or approach or instrumentation that has flown. These are all suborbital field campaigns. And if you make them big enough, sure, they look like they cover the world. But also, if you look very carefully, there's only a subsection, namely these blue ones that are focused on aerosol cloud interactions. What's most notably missing is that we, the US, has not flown a dust experiment in forever. That Pride experiment that June mentioned was here in 2000 or 2001, I believe, or 2000, I believe. And we have not flown anything in a long time focused solely on dust, which is probably an oversight. Okay, I'd like to shift gears and talk about this NASA mission that's now called Atmos. It used to be called ACCP. As I mentioned before, it was motivated by the Academy's 2017 Decadal Survey. It was focused on aerosols, clouds, convection, and precipitation, and the priorities for observables were identified to be vertical profiles of aerosol properties and cloud properties, and also vertical motion, if at all possible, with the Doppler-based radar systems. So they had a set of questions that needed to be addressed with this kind of observable capabilities. On the aerosol side, we try to focus on 4D aerosol distribution, sampling, and lifetime, although there's no doubt in my mind that we will never get from remote sensing information that is similar to what I talked about, this, for example, this carbon loss. But there may be ways in which we could inform the prior assumptions that go into the retrievals. Aerosol amounts and aerosol properties as they drive radiative effects, aerosol cloud interactions, and even air quality in as far as possible will be looked at. Here's a set of goals for cloud feedback, storm dynamics, cold cloud and precipitation, aerosol processes, and aerosol impacts on radiation, and how they break out further into objectives, which then translate into geophysical variables that have to be observed. I don't mean for you to study this in detail, but it's about as broad as one can imagine retrieving from remote sensing. And again, on the aerosol side, the idea was active remote sensing from a LiDAR augmented by some passive remote sensing, likely from a polarimeter. Okay, I will skip over that. This is, you know what retrievals look like. The group that we were part of was called the Science Impact Team, and we focused on level 2 retrievals. And we did this for a combination of candidate instruments, more or less capable LiDARs, ranging all the way from simple backscatter LiDARs like a CATS or a Colloquium instrument to all the way an HSRL2 instrument, multi-frequency, high spectral resolution capable retrievals. And then there was a LiDAR working group that's focused more on instrument performance and design requirements. And we ran a whole list of retrievals based on canonical cases. Feng Zhu and Lan Gao is on the line here, did the main retrievals on the OU side in combination with 4 or 5 others. And this is the final recommended architecture that the study team provided to NASA headquarters and proposed. So the study will include a polar satellite that will have a Ka and W Doppler radar, microwave radiometer, an HSRL type LiDAR, a polarimeter, thermal infrared spectrometer, and a UV vis spectrometer. And then there will be 2 satellites in the inclined orbit, one with a WK U-band Doppler radar, a stereo camera for vertical motion, and also a polarimeter and a backscatter LiDAR on the second inclined orbit satellite. So a very ambitious concept. And after all is said and done, the only thing that fit into the cost envelope was an HSRL1 type instrument with two extinction, 1 extinction capable, 2 backscatter, and 2 dipole channels essentially. So I won't go over the details of this. Suffice it to say that for every one of the geophysical variables that you looked at, we ran the forward simulations in a fully consistent way, modeled the scenes and the LiDAR signals, and then tried to see which instrument combination can retrieve the geophysical variables within the uncertainty requirements that were put forward in the traceability matrix. And to no surprise, the HSRL2 system given in green in most cases provided the highest capabilities. Here, what you're looking at is for different scenes, nadir at day, nadir at night, and off nadir at day. You're looking at the fraction of simulated retrievals that were within the target uncertainty of the SATM. And you can see that in almost all cases, the HSRL2 system plus a polarimeter performed the best in terms of ability to retrieve the geophysical variables. Okay, I'll close out and take 2 or 3 minutes to talk about the School of Meteorology, if that's okay. We have a messaging issue on our hand in that the School of Meteorology at the University of Oklahoma has traditionally been known for mesoscale meteorology, radar and severe weather, some boundary layer studies, and some numerical weather prediction, including data assimilation and ensemble forecasting. Over the last 6 to 8 years or so, people were hired that arguably work far from those traditional strengths, and they do climate variability in tropical climate, air quality, clouds and aerosols, polar meteorology, hydrological cycle, a lot of remote sensing. But the school is just not known for them yet because the majority of these people were rather young. Future expansions are towards subseasonal to seasonal forecasting. We want to do a lot more composition. We do want to strengthen our high impact and severe weather, which is our traditional strength, because we've done very well with that. But again, we have future additions in Earth system modeling. It's essentially at all scales. We do think about bringing a physical oceanographer, tropical cyclones, and more atmospheric chemistry. Those actually were 2 recent additions. We had made 2 hires last year. And then these other ones here, these other ones are pointing to were recently identified as hiring priorities. So we're working on a set of cluster hires over the next 3 years. The first one will be in high impact weather, including chemical weather, which would be relevant for the group and the young folks that are on this call. So look out for a hiring announcement in a cluster format. And then in FY23, we hope to have an S2S, a subseasonal to seasonal cluster, which would include ocean, land, atmosphere modeling. And then in FY24, a full regional to Earth system modeling cluster with many foci, including carbon cycling and biogeochemical modeling. We have just finished, or we are about to finish a new strategic plan for the school. I'll just highlight the 4 major goals, and it starts out with cultural proficiency. We want to promote a culture that fosters justice, equity, diversity, and inclusion. And we do want to become a proactively anti-racist community. That's not to say that we are racist at this moment. We're inherently racist, similar to the reckoning that is happening in this country by not removing barriers for underrepresented minorities in our program. And we want to do better in that. The other goals are focused around research, education, and the socioeconomic welfare of the nation and the world. But the school is hopefully transitioning. I will put up some conclusions. I won't bore you with the details. I've harped on many of these, but there remain pretty big gaps in observations for aerosol properties and their usefulness for constraining models. These detailed suborbital measurements fill some of the gaps regarding the processes, but we have to be very careful with their representativeness. Some of the instrument capabilities are rapidly advancing, and that's an important part of the puzzle of how we do better with models. And as I said, the NASA Atmos mission, formerly ACCP, is going to target a whole bunch of aerosol properties as key observables that will hopefully give us insight into how to improve some of the models. By improving the measurements, of course, that's always the point. And we have some preliminary simulations that give us a lot of confidence, in particular these joint retrievals of LiDARs and polarimeters, giving us some of these insights. So with that, I'll stop, and I'd be more than happy to take a bunch of questions. I went fairly long here. I hope that was okay.
Thank you, Jens. Very comprehensive and insightful talk. So I like to have an audience to give you a round of applause to Jans first, before I end the recording here, and then we can open up the questions and discussions. So if you don't know use Zoom, you can on the lower right corner, there is a reactions. You can give Jans a round of applause there.
Appreciate that.
Yeah, thank you. So I'm going to stop the recording here.